Hello, my name is Dylan Hacker, and today I will be showing you the maximum angular frequency at which you can rotate a cylindrical cup without any spillage. So starting off, I'm going to draw the situation. So we have our cup with an amount of liquid in it. To keep things simple, I'm just going to say the height of the liquid is going to be equivalent to the radius of the cup. So those two are going to be known as big R, and of course this is when the cup is sitting still in this drawing. In just a moment I'll draw it when it is spinning. That is the cup with the liquid inside of it when it is rotating at the maximum angular frequency. And I drew two dotted lines on each on the situations, and the volume under and above the lines will be equivalent in each situation. So this volume and this volume will be equivalent, and the two green ones will be equivalent as well, and I'll touch on that in just a moment. The height of the cup will be known as big H, and the height from this dip point to the top of the cup will be known as H, little h. So to find the total height of this cup, we will need to take R minus, I'm going to call this from that right there, I'm going to call that D, the difference from the dip. So this R value is going to be R minus D. That'll give us to the dotted line, plus the height at big R when R equals big R. And the little r is going to be referring to the radial point, which I will be describing in just a minute as well. So now that we have that cleared up, to begin, we want to start by finding this H at radial point of the radius of the cup. So to start that, we know that the basic law of statics is the change in pressure over the change in radial point is equal to rho, which is the density, times the acceleration, which in this case it's going to be omega, which W is going to be omega, times R. Alright, and once we have that, we're going to integrate both sides. The boundaries of integration will be from 0 to P, and you notice that we have P in both the boundaries and inside, so we're going to make a dummy variable. So we're just going to call that prime, and we'll do the same thing on the right side. Alright, and once we integrate this, we will get the P, the pressure, equals rho omega squared times R squared over 2. So we also know that pressure at any point underwater is equivalent to rho GH. So we put those two equal. The density rho will cancel out on both sides, and we get H at any radial point is going to be equal to omega squared times R squared over 2G. So now we have that, we want to find it at big R, which is the radius of the cylinder. Alrighty, now that we have that, we can work on our other variable that we need, which is d. Now to find this difference, we know that the volumes on both will be equivalent. So the volume on this left side can be found by the volume equation pi r squared times d, which is the height. This is equal to the volume of this right there. Now to find the volume of this weird shape on the right side, we're going to cut it up into little pieces and take the delta V of each. So we know that this, say this is at some radial point R, we know that we can find that by taking the dV, delta V, times 2 pi r h, which is the circumference, times dr. And to make this a little bit more sense, I'll view it from the top view. So we have it at some r, and these two, they're the same picture. The left side is the side view, and on the right side, this is the top view. And to find this, we use this equation right here. Now we have to plug in h from our equation over here. And we get 2 pi omega squared r cubed dr. Now we want to integrate this. The boundaries on the left is going to be 0 to V, which is going to be the volume of the liquid. And on the right, the area of integration, the bounds of integration, is going from 0 to big R, which is going to be the radius of the cup. So we get V equals, oh, I forgot the 2G up here. This is over 2G. Those twos cross out. And we get omega squared r cubed over 4G. Now we can go back and plug it in to find D. So we know that the volume is equal to that right there, equal to the volume on the left side of the cup, which was standing still, which is pi r squared, that was really bad, pi r squared times D. And now we just solve for D. The pi's cancel, forgot the pi. Yep, I just forgot the pi. Pi's go ahead, cancel out. This becomes a 2 right there. So we get D is equal to R squared omega squared over 4G. So now that we have that, we can plug it back into our height equation. So little h. So we get height equals R minus this value of D, which is omega squared R squared over 4G, plus h, little h at the radius of big R, which if we remember is omega squared R squared over 2G. So I'm going to move the R onto the left side and simplify this. We get h minus r equals omega squared r squared over 2G, or 4G, apologies, 4G. So So we get omega squared is equal to (4g times h minus r) over r squared. We want to take the square root of that. And we get omega, which remember is our angular frequency, is equal to 2 times the square root of g times h minus r, the height of the cup minus the radius of the cup, over the radius of the cup. Using that equation, you will be able to find the maximum angular velocity at which the cup will be able to rotate with no spillage. Thank you so much for watching. Enjoy the rest of your day.